Today we're going to look at the next family of functional groups, and that is the alkenes, which are hydrocarbons with a double bond. So alkenes, we call them unsaturated hydrocarbons. So the alkanes, we consider them saturated because there's no more places to put hydrogen on them. These ones are unsaturated because we can add things across the double bond. The presence of the double bond in an alkene makes them considerably more reactive than an alkane. Okay, so we have a bunch of electrons built up in the same area, so a very electronegative region on these molecules. Okay, so this is a lot of charge built up in one spot. It makes it very attractive to what we call electrophiles. So an electrophile is something seeking electrons or seeking that negative charge. And it enables it to polarize approaching molecules. We'll see this a little bit later when we get into the actual reaction mechanisms, why that polarizing of other molecules is important. Um, Alkenes are used as a major industrial feedstock. So what that means is that an alkene is essentially the base molecule for all organic synthesis pathways or organic synthetic reactions. If you want to so the goal when designing, say, a new pharmaceutical drug or any new organic compound, a goal is to try to be able to synthesize that compound from the very simple alkene, ideally ethene, if possible. Okay, so they're the basis of a lot of different reactions. And alkenes undergo addition reactions. So essentially that double bond, we can add things across both sides of that double bond. So it leaves us a lot of different options and a lot of different reactions for what can be added to these molecules. The first reaction is the addition of hydrogen. We call this hydrogenation. Okay, so at the top we have the general reaction, C2H4 plus hydrogen. So we add the hydrogen across the double bond. See here what happens. This carbon on the left here currently has two hydrogens. This one has two. One of these hydrogens from the H2 gets added to one side of the double bond. The other one gets added to another. So in this process, we're going from an alkene, ethene, to an alkane, ethane. In order to perform this reaction, to go from an alkene to an alkane, we have to heat it. So it requires reaction conditions of up to 180 degrees Celsius and a catalyst, in this case nickel. There are other catalysts that can be used, like palladium, for example, but nickel is much cheaper. So you're not spending a ton of money trying to get and reuse the palladium catalysts. This process is particularly important in industry. One example is converting unsaturated vegetable oils to margarine. So I believe it's actually sunflower oil, which is why you'll see the pictures of sunflowers on margarine containers. That oil is an alkene. There's many alkene or double bonded carbons within the oil. So you take that, you hydrogenate it, so you add hydrogen across those double bonds, creating more singular bonds. So you increase the saturation, making it more like an alkane than an alkene, and that actually makes it the boiling point go up. So we get the or the melting point go up. Sorry. So we get solidification occurring, and we have margarine as opposed to the vegetable oil. So the second reaction is the addition of halogens, which we call halogenation. In this case, we take ethene again plus bromine, but you can add any halogen. You can add fluorine, chlorine, or iodine to make 1,2-dibromoethane. Okay, so the bromine, like the hydrogen in the previous example, one bromine gets added across each side of the double bond. So one carbon picks up one bromine, one carbon picks up the other. This reaction actually requires no special conditions at all. If you just take an alkane and take some bromine and mix them together, this reaction will occur quite readily at room temperature. In fact, we use this reaction as a test for alkenes. So if you have a mixture of hydrocarbons, for example, an environmental sample, and you want to know if we have alkenes in it, which we don't particularly want in the environment because organic compounds can be quite toxic. Okay, you take your sample, you take what you have, you mix bromine in, and you shake it. When the bromine reacts, bromine water is a bright orange color. When it reacts and bonds to the alkene, the bromine leaves from the water, creating the bromoalkane, which is a colorless compound. So you'll go from an orange to a colorless. So this lets us distinguish between alkanes and alkenes. Now remember though, you would have to do this not exposed to UV light, because if we exposed it to UV light, the alkane would also react through the free radical substitution mechanism we saw in the previous video. So we can use this not exposed to light to distinguish between alkenes, which will react, and alkanes, which will not. The third reaction, very similar to the last, is the addition of a hydrogen halide. So it's still considered halogenation because we're adding a halogen. But in this case, instead of adding Br2 like we did in the last example, we're adding HBr. So the hydrogen will go to one side of the double bond, and the bromine will go to the other side. It's actually specific on which side it'll go to, but we aren't going to get into this until the more advanced part of the chapter. So just know that it adds a hydrogen and a bromine to either side of the alkene, creating a halogenated alkane. Okay, and again, this reaction, like the previous, occurs with no special conditions required. The fourth reaction is the addition of water. And this is the process of making an alkene into an alcohol. So we take our alkene, ethene, we add steam. So the water does have to be heated steam. It can't just be liquid water. It will not react. It needs to be hot. And we take concentrated sulfuric acid or phosphoric acid, which acts as a catalyst, to produce ethanol, so an alcohol. So we see in the schematic here, we have our water. So water being an oxygen and two hydrogens. Okay, the one hydrogen bonds to one carbon, and the alcohol group that's left bonds to the other carbon. So that's what creates the alcohol. So again, we have to have steam and a phosphoric or sulfuric acid catalyst for this reaction to take place. This is actually, so the ethanol that we use in the lab, the big bucket that we have, this would be the process used to make industrial ethanol. For using the fermentation process from sugar, which you would use to make drinking alcohol, would be incredibly expensive to produce the amount of ethanol needed in industry or in labs. So we use this process instead. It's much cheaper to get it in mass quantities. The fifth reaction is addition polymerization. So we can use alkenes to make polymers. Now polymers are incredibly important, and you come across them, you use polymers, you come across them every day of your life. So anything plastic or, like I said, oils, well, not quite oils, but any plastics are polymers. Okay, so under the right conditions, molecules, which we refer to as monomers. So for example, here is one monomer. Here's a second monomer. Here's a third monomer of one bromo-2-fluoroethane. So we have three monomers. They add together, creating a polymer, meaning many mers or many units. They bond using the double bond. So one piece of the double bond will break and attach to this carbon. But wait, this carbon now has 5 bonds. This bond breaks, now it has 4, attaches to this carbon, this bond breaks, attaches to this one, so on and so on. And we get this repeating chain of monomers. Okay, in this case, we have one bromo. So if we were to number our carbons here on the monomer, one bromo, 2-fluoroethene. When it polymerizes, we change the name. All we do is put the name in brackets and add poly in the front. Nothing else from the name changes. We still keep the ene ending, even though there's no more double bond technically. That doesn't change. We just put poly in front, and that's the name of our polymer. The reaction conditions, you don't have to know any specific ones for this. It does vary from alkene to alkene, but generally is high pressure, temperature, and a catalyst. Okay, so the carbons in the double carbon bond are what form the carbon chain. So nothing else partakes in the chain. The rest of the things just hang off the edges of the chain. It's only that double bond that contributes to making the polymer. So let's take a look at how to draw a polymer here. So we'll look at propene. We'll just draw a 3 unit. So here's our unit of propene with our double bond here that's going to be used for the polymer. Now what I'm going to do is draw this in its skeletal form. Okay, so we have one propene here. Okay, so we have 1, 2, 3 carbons with our double bond and our group coming off the top here. Here is our second propene. Here is our third propene. So when we draw these together, what's going to happen is this double bond is going to go and bond to this carbon. This double bond is going to go and bond to this carbon. This double bond will go and bond to a carbon, so on down the chain. And what we get, okay, so we have 2 carbons here, carbon that were previously double bonded here, okay, and they have a methyl group coming up off of the second one. This double bond then went on to bond to the next monomer, which will be a carbon and a carbon. I'll add the hydrogens on in a moment with a methyl group coming off the second one. And this then went to connect to the next monomer, which again is the same thing, a carbon and the methyl group coming off of the second carbon. And then there would be other ones on either end of the chain that continue this bonding. Then we can add in our hydrogens. Okay, so this is what it's like, the process of drawing a monomer. Now what you also have to include, so this is an example of drawing it with 3 units. What you also have to include are square brackets around this. And you put an N down at the bottom right, and that means that this is repeating over and over again for some amount of time. Okay, so that's one example of propene. Let's take a look at another example. This is phenylethene, which is also known as styrene. Okay, and it makes polystyrene or styrofoam. So here's our monomer. Okay, so we have a C double bonded to a C, and we have our benzene group coming off the bottom of the first C there. Okay, so it looks like this, and then there would be a hydrogen here, and a hydrogen here. And again, what's going to happen? So we'll draw a couple of a 3 monomer chain of this polymer. We have our benzene, and one more. Okay, and the same thing happens as before. So our double bond will break, attaching to this carbon. This double bond breaks, attaching to this carbon. This one breaks, attaching, and there would be one from over here somewhere that would attach here. And we produce our repeating chain. So now we have every second carbon is going to have a benzene group. So again, here is one monomer like we have to the left, which is then bonded to a second monomer of the same thing. I'm going to alternate the sides of my benzene just to save some space. And just imagine for a second that there's 3 of them here. I'm not going to have enough space to draw a third. But again, just like before, we would put this in square brackets. This is a 2 monomer repeating unit, and we put it in square brackets, and we put our N here, representing that this is a repeating unit. Okay, and we'll do one more. So we'll look at pent-2ene or polypent-2ene. Okay, so pent-2ene, I'm going to do this one as a skeletal structure. So our monomer that we have our double bonded carbon. Coming down, we have a methyl, and coming up, we have an ethyl. Okay, so we have 3 of these units. That are repeating. Same thing as before. One double bond breaks and attacks, and one from over there. Okay, so in our chain here, our 3 repeating units, we're going to have 6 carbons. sorry, I'll draw the bonds to each other carbon. So 1, 2, this would be the new bond that's created. This would be the new bond. So we'll create a new bond, and from over here, coming down off of those carbons, here is our methyl group, and here is our ethyl group off the top. And of course, we have to put it in brackets. We have our 3 repeating units. We put our end down there to show that it is a polymer. So this is what we would do to draw the polymer in a skeletal structure rather than drawing out the full thing in its full molecular formula. Okay, so as a summary, here's our alkane in the center. This is the beginning of a very large chart we're going to do to sum up all of our organic reactions. But here's ones for alkenes specifically. So we have our alkene, and here's all the different reactions it can make. So the first one we looked at was our hydrogenation from an alkene to an alkane, this bottom arrow here. Okay, it requires adding hydrogen and a nickel catalyst and using a high temperature, so up to 180 degrees Celsius. We then looked at the halogenation, okay, which is our bromine. Adding our bromine across, halogenation requires no special reaction conditions, or does the halogenation to the halogenoalkane with just one halogen by adding HBr. The color with the bromine one, again, we could use this for the bromine test because it will, when it reacts, it goes from brownish orange to colorless when it reacts with a alkene, but does not react with alkanes. We had our alcohol. So the addition of water goes from an alkene to an alcohol using concentrated sulfuric or phosphoric acid. And lastly, our addition polymers, where we have many, many different addition polymers to count from.